Good afternoon. My name is Willem Slabbert and I'm the specialist for samplers and magnetics at Multotec. Today we'll be discussing when grinding too fine can actually have a negative impact on your unit operation and your overall process. As part of the contents, we'll discuss a bit on the wet drum magnetic separation theory. Thereafter, we will run two case studies. The first case study will discuss an opportunity where it was indeed needed to grind finer to get the most out of the wet drum magnetic separator. And the second discussion is all around when you grind too fine, you could actually decrease the overall efficiency of your magnetic separation equipment. So the first important slide is only one equation for the day, is that your magnetic force experienced by a particle is equal to the material's magnetic susceptibility. The second parameter to our equation is the overall particle volume. The magnetic flux density, as well as the gradient of your magnetic field, plays an important part. If we have a strong magnetic field but no gradient, particles won't be moved towards a certain surface of the magnetic separation machine. The gradient of the magnetic field is therefore very important because it acts as the driving force that attracts particles onto the separation surface of the relevant equipment. The second important principle for the day is a phenomenon that occurs only on ferromagnetic particles, not paramagnetic particles, where if those particles are exposed to a wet drum magnetic separator, and on the inside of the drum we have a magnetic circuit protruding through the surface of the drum and into the slurry section, which is the working volume of this machine. As soon as a ferromagnetic particle enters the magnetic field, that particle develops a magnetic field around itself. If we introduce more particles into the magnetic field and at close enough approximation to each other, those two particles will attract each other to form an even larger magnetic field. This process would then occur until longer magnetic chains of particles are formed. Finally, those chains would interlink, creating an effective larger particle volume, which according to the magnetic force equation would then experience a larger force of attraction towards the wet drum magnet surface, where finally the particles, as part of the separation process, will be separated from the non-magnetic particles, and in the case of a wet drum magnetic separator, that occurs by the rotation of the drum towards the magnetic concentrate. The last important point for today in terms of the theory of magnetic separation is that wet drum magseps are capable of recovering very fine particles, as seen by the graph here. Only the ultra-fine particles in the range of around 17 micron would typically be lost through a wet drum magnetic separator. Even though these particles will form part of the chains within the magnetic flocculation effect, as soon as a larger equally magnetic particle enters into the magnetic field, that particle would kick out a smaller particle, and that smaller particle would eventually be washed out of the machine, being replaced by the larger, slightly more magnetic particle that would then form part of the chain and would overall be recovered by the machine. So with the theory concluded, let me present the first case study to you on an ore body in Zimbabwe, which is on the Great Dyke ore deposit, running from north to south across most of the country of Zimbabwe. And this particular ore was just east of the town of Kwekwe. Some of the characteristics is that the ore was typically weathered from the dike protrusions, the hilltops, into a rift valley. This is, in other words, an alluvial deposit that was exposed to quite significant weathering over the years, and as part of the weathering, the material was liberated to an extent from the hard rock and washed down into this rift valley, where it is mined in an open cast fashion as low as 0.5 to 2.5 meters deep. The main minerals in this part of the deposit was chromite, which in this case is the target mineral under discussion. There are also a lot of silica minerals, including enstatite and serpentine. There are ferrous minerals but at various oxidation states, depending on the weathering of that particular zone over time. And that weathering could be different from one hilltop to the next. Then the others are copper and PGMs, but in this specific part of the ore body was only present in very low concentrations. So in that suite of minerals, I would like to highlight the magnetic susceptibility of a number of them. In terms of comparison, the very first bar that we list is the magnetic susceptibility of iron, either as pig iron or as rolled formed steel, followed then by magnetite, which is again highly ferromagnetic and would be exposed to the magnetic flocculation force. Ilmenite presents itself naturally in two different magnetic susceptibilities, one being extremely low and the other one quite high, comparable then to magnetite and iron. Chromite would be regarded as a paramagnetic mineral along with hematite, but as can be seen from the graph, chromite would typically be more susceptible to magnetic force separation than hematite. The value proposition of this particular ore is that after processing, the ore would exhibit a very high chrome to iron ratio, typically greater than 2.0. That, compared to other ores that are available in South Africa, would only exhibit a chrome to iron ratio of around 1.2. Furthermore, the chromite in this particular ore in Zimbabwe, in the Kwekwe region, yielded as high as greater than 55% chromite measured as Cr2O3, again compared to local ores at around only 42%. And a final benefit of this particular ore body is the beautifully natural chromite crystals that would look similar to the pictures on the right. Commercially, this ore is high in demand and would typically have a 30% higher price than any of the chromite ores mined in South Africa. The flow sheet around this case study you have seen before today in a different presentation, and this flow sheet is the resultant flow sheet after some optimization work done in the previous discussion, where we have first of all a desliming cyclone in the circuit, sending the ultrafine material to a final tails stream. We then have 4 different stages of spirals that would concentrate up the chromite as well as any other fast settling, either dense or coarse material, finally into a scavenger circuit included as well, and finally we would have a recleaner spiral producing a heavy minerals stream. That heavy minerals stream, with the addition of some dilution water to optimize the feed conditions to the wet drum magsep, would then be sent to the wet drum magnetic separator to separate any ferromagnetic minerals from the stream and result in a cleaner chromite stream at the end of the process. So the purpose of the magsep is, after the 4 stages of the spiral, is to decrease the iron grade that is presented to the magsep by removing a ferrous fraction to the magnetic product stream. Chromite, on the other hand, has a much lower magnetic susceptibility and typically would not respond to the low intensity magnetic field that is presented by this magsep. In other words, in this application, we can regard the chromite as a non-magnetic mineral when it is processed through the magsep. As we separate the ferrous fraction off to the magnetic concentrate, we would conversely also produce a non-magnetic product stream, which is then deprived of some of the ferrous minerals. In other words, we could increase the chromite grade in the non-magnetic stream, which will also boost the chrome to iron ratio. As a secondary benefit of the magsep, we also noted, despite the 4 stages of spirals prior to the magnetic separator, there was always very coarse silicas that still reported to the concentrate stream, in other words, the heavy stream of the spirals, and which was difficult to remove. After the magnetic separation, however, once we've changed the mineral composition going on to a final spiral stage, those heavy silicates, which were typically coarse and despite its lower density had a fast settling velocity because of the particle size, would then separate out because the feed to the final stage of spiral in composition would be different to the other 4. The table below shows the typical mass splits and the performance of the magnetic separator with regards to the different minerals that were present in this ore body that was fed into the magsep. The first point to note is that the solids mass split across the magnetic separator is around 46% to the magnetic stream and 54% to the non-mags. That is quite significant, and indeed the stream is quite well split into a magnetic and a non-magnetic fraction by means of solids mass pool. The second area of focus showed in the yellow bubble in the table down below is that the iron grade in the non-magnetic stream has definitely been reduced as per the purpose of having the magsep installed in this part of the flow sheet, taking the feed concentration of 25.8% down to only 16.3% in the non-magnetic chromite-rich product. Secondly, in the blue bubble, we do note that the chromite percentage and grade in the non-magnetic stream has significantly increased from 36.8% in the magsep feed all the way up to 58%, thereby exceeding the target of 55% by at least 3%. The chrome to iron ratio is also significantly upgraded to a 3.1 ratio where the target was 2.5. When we consider, however, the chromite content in the magnetic tailing stream coming from the magnetic separator, we do note that there is a fairly high grade of chromite still present in that stream. That was a concern to the client because they believed that we are losing yield to the tailings of this plant and not capitalizing fully on the chromite that is available in the ore. One possibility and mechanism that could explain the high amount of chromite in the magnetic product from the magsep is that in the thick cake of magnetite or ferrous material that got attracted onto the drum surface, there could be entrapped non-magnetics throughout the 50 mm thickness of material that formed on the drum surface. However, if we consider the silica fraction, which is also a non-magnetic element then within this mechanism, we note that there is 0.0% silica in the magnetic tailings stream. That means that the magsep is delivering a magnetic stream that is free of any non-magnetic materials. How then would we explain the amount of chromite that we assume to be liberated in this case from the weathering, natural weathering of the dike material to be present in the non-magnetic stream? So when in doubt and we need further investigation, we sometimes have to zoom into the finds to get an answer. And this is where our kind colleagues at the University of Pretoria conducted some scanning electron microscope photos on the two different product streams for us. So what we have in the figure is a scanning electron microscope photo of the magnetic tailings fraction. This photo shows us on the lighter fractions of it that there is significant chromite still chemically bonded to the ferrous fraction, in this case assumed to be magnetite. The next photo shows us the non-magnetic stream where we would expect a lot of chromite being enriched by the removal of the ferrous fraction to the magnetic product. But this photo shows us again in light wonderful chromite crystals, but the darker particles are fully liberated, again some form of ferrous mineral. So even though our magnetic separator achieved its purpose of separating the ferrous fraction from the chromite and successfully upgraded not only the chromite concentration or grade but also the chrome to iron ratio, there are chromite yield losses to the magnetic tails. Despite the initial belief that the material is liberated, we do see that there is significant chromite still bonded to the ferrous fraction of magnetite. Furthermore, there are also ferrous-bearing minerals within the non-magnetic stream, which indicates a ferrous iron mineral that is not of the same order of magnitude in terms of its magnetic susceptibility, and it behaves as though it is non-magnetic when exposed to a low-intensity magnetic field. The scanning electron microscope photos showed that it is possible to further liberate the chromite from the paramagnetic fraction. However, in this case, milling was not a commercially viable option for this very rich deposit. In other words, there is still chromite that is leaking to the tailings of our plant here, and it's important to sample that material going forward so that one day you could accurately quantify the value of the resource that still remains in the tails. The second case study revolves more particularly around vanadium. In this slide we see that South Africa is a major contributor to the overall vanadium reserves in the world, and we further note in the text below that around 85% of the globally available vanadium is associated with a titaniferous magnetite fraction. In this case, that would mean that a magnetite mineral has bonded titanium in the form of ilmenite and also some bonded vanadium to the magnetite, and from the magnetite then the ilmenite and the vanadium can be recovered. We further note that the global average is around 1 to 1.5% of vanadium within the run-of-mine or reserve as grade. The ore body under this case study under discussion is the Bushveld Igneous Complex, and more particularly the Eastern Limb. The vanadium deposits within this region is typically found in the upper zone of the geology and is indicated on the slide by the dotted blue lines running on both the eastern and the western limbs of this material. The specific material that we tested for this case study was weathered ore from the eastern limb, where again material was weathered from the outcrops into a flat valley that could be mined by open cast method at between 0.5 and 3 meters deep. It is a vanadium bearing titaniferous magnetite sample. The main minerals within the ore is typically PGMs, iron, again at various degrees of weathering and associated magnetic susceptibility, vanadium, titanium, tin, and also some chromite. The value proposition of this ore body is that globally vanadium is quite a scarce and valuable mineral. It also, where it is found, reports itself only in very low concentrations. Vanadium alloys have superior shock resistance, is lightweight, strong, and typically used as aerospace materials. In the conventional flow sheet of titaniferous magnetite processing, one would typically take the milled ore onto a LIMS machine running at 0.2 Tesla or 2000 Gauss. From there, the magnetite will be recovered by this machine, but bonded with the magnetite would be the vanadium. In the LIMS non-magnetic product, that stream would be sent to a WIMS that would typically run at 0.8 Tesla or 8000 Gauss to produce a magnetic ilmenite product, and finally a non-magnetic hematite product also rich in silica that would form the tailing stream of the overall process. The resultant flow sheet from the below discussion in this case study is a feed material that is screened at -2 millimeters, fed into a magsep at an optimum 20% solids by mass, and through a MIMS machine, not a LIMS machine. In this case, the MIMS machine had a magnetic intensity of 6500 Gauss to produce a stream of magnetite with bonded vanadium still within the magnetite matrix. The non-magnetic stream is also sent to a WIMS, but due to very poor magnetic responses at 8000 Gauss, which is the conventional operating parameter, the WIMS was run at 1.0 and 1.3 Tesla respectively, and produced an iron mineral with bonded vanadium and ilmenite and a non-magnetic tailing stream consisting of other minerals. As we can see, this is the typical low-grade ore, and the ore did not respond to low-intensity magnetic separation at all, which is why we used a 0.65 Tesla MIMS machine of medium magnetic intensity. The first important point to note from the results below, tabulated results below, is the mass yield through the MIMS percent towards the magnetic fraction was only 10.2%, while the material reporting to the non-magnetic fraction was the balance of 89.8%. We do note that the iron is significantly upgraded from a feed grade of 30% to around 80% into the magnetic fraction. We further also note that the vanadium grade is significantly upgraded in this fraction from 0.26 to a grade of 1.1, again with the associated magnetite fraction in the magnetics product stream. The silica grades are quite low, in the magnetic stream only 1.5%, indicating a good separation with a clean magnetite concentration and very little entrapped silica into the magnetic product. Yet, the recovery of iron to the magnetic product is quite low, only 27 or so percent. Therefore, the mineral might not be magnetite purely, but may have other oxidation states, for instance hematite, or one of the various other oxidation states that exist in naturally weathered ore between magnetite and hematite, each having their own unique magnetic susceptibility. We further note that more than half of the vanadium reports to the non-magnetic tailings of the wet drum MIMS machine, and therefore there is still significant value in that stream that has to be further processed. The results tabulated below shows the results that we achieved while running a WIMS machine at 10,000 Gauss. The solids mass split is only 6% towards the magnetics, with around 54% accounting to the non-magnetics, and the remainder of that balance stream reporting either as middlings or overflow. I would like to explain the overflow percentage here, which is quite high. The machine has to have a certain slurry level to operate efficiently, and when we do test work we want to ensure the efficient operation, and we would rather have more overflow than have less overflow, in which case the magnetic separation efficiency would have decreased significantly. We can however conclude that the iron, the vanadium as well as the titanium upgraded into the magnetic fraction as shown in the bubbles in yellow. However, the recovery of all three of these minerals were in the same order of magnitude, around 12 or 18%. We can also conclude that the separation between the ilmenite and the hematite is quite poor, and that the two minerals report together in terms of their recovery towards the magnetic and the non-magnetic fractions respectively. Next up, we ran the WIMS at a maximum of 1.3 Tesla. As we know in the mining and minerals industry, if something doesn't work, we take out our big hammer, and in this case we ran the machine at absolute maximum, giving it the best chance of achieving a successful separation with good mass splits. From the tabulated results we can see that the mass split was around 50% to the magnetic fraction. The iron, vanadium and titanium again upgraded into the magnetic fraction, which is good news given the much improved mass split that we have achieved. However, the iron, titanium and vanadium recovery are again all within the same order of magnitude, around 80 to 95%, compared to the previous table where the recoveries were all of the same magnitude, being either 12 or 18%. In other words, the mineral separation is not very effective. We can conclude that the iron, the vanadium and the titanium, despite their different magnetic susceptibilities, all report with the same recoveries to the magnetic and non-magnetic fractions, and therefore we can conclude that the material must still be chemically bonded. In this case, there would be a benefit to further liberate the material through a finer grind. Consider that we had only -2 material, which is quite a coarse fraction, fed into this process. But the big question is, what size do we liberate to? Because there was no further information on this particular ore and mineralogy, we therefore had to consult literature to possibly find an answer towards the liberation size, where if we expose the minerals through the same magnetic separation process, we would have a separation of that minerals through the machine. So a technical paper compiled as early as 2017 showed that on a Chinese titaniferous vanadium bearing magnetite ore, also a low grade ore with significant weathering, which is quite similar to our ore body under question in this case study, had the following mineral composition. There was some magnetite, but the ferrous fraction in this Chinese ore was mostly martite. Also, quite a good percentage of ilmenite was available in the ore. Do note that the magnetic susceptibility of the magnetite is far greater than the magnetic susceptibility of the martite and the ilmenite, and that the susceptibility of the last two mentioned minerals overlap quite significantly in that range. The authors then went on to test the behavior and the magnetic response of the material at different magnetic intensities through a WIMS machine, and found similar results to the results we've reported on this case study, whereby if you increase the magnetic intensity, you get an increased recovery on all minerals across the range of magnetic intensities tested. So from this conclusion, it seems then that these minerals are also bonded to each other and are also difficult to separate. They therefore did some more work on the liberation size. In this graph, on the x-axis, we note that moving from left to right, the particle size distribution being smaller than 0.074 millimeters or 740 micron increases as we move. That means further towards the right side of the graph, the overall material grind is much finer. As expected, we do see a decrease in recovery of the iron ore read off the right hand side of the y-axis as the material becomes finer. This is in line with theory, where finer particles experiences a much lower magnetic force acting on them. Further consider that the magnetic flocculation effect does not apply to paramagnetic minerals. It only applies to ferromagnetic minerals. Therefore, in this case, as material becomes finer, it will experience a lower magnetic force, and more of that material will be washed out of the magnetic separator as non-magnetic tailings. As we further liberate the material in the case of iron, we note that the grade of iron slightly increases as the material becomes finer. When we consider the ilmenite or titanium fraction of this ore, we again see that the overall titanium recovery decreases as the material becomes finer, but the grade of the titanium reporting to the magnetic fraction also decreases as the ilmenite is liberated and is being washed to the non-magnetic side of this WIMS machine that was tested. The recovery of vanadium also decreases as expected. However, the grade of the vanadium has a very interesting trend where the overall recovery of the vanadium increases to around 85%, passing 740 micron. This indicates that the vanadium below 740 micron at 85% passing is still bonded to the ferrous fraction, but grinding the material finer than that liberates the vanadium from the iron fraction, and the vanadium is then overall lost to the tailings. The iron, titanium and vanadium recovery follows the same downward trend for all of these graphs reported by the authors. However, the grade of the iron ore continuously increases as the iron ore is further liberated from the ilmenite and the vanadium. It is expected then that finer grinding could liberate the ilmenite slightly earlier, and therefore the separation could be done to recover the ferrous fraction with the vanadium while selectively losing the ilmenite to the tails. However, grinding the material too fine would also liberate the vanadium from the ferrous fraction, and because vanadium itself is not magnetic, that vanadium would then not recover with the ferrous fraction, and the valuable vanadium would be lost to the tailing stream. As a conclusion to the presentation and both case studies, even though magnetic separators are highly successful at processing ultrafine material in the low intensity, medium intensity and high intensity magnetic separation ranges, finer grinds are first of all not always feasible as determined by case study number 1, and in case study number 2, grinding too fine could liberate potential valuable minerals that should be recovered with the ferrous mineral, to the extent that the valuable minerals can then be lost to the non-magnetic tailings. Optimum liberation sizes may exist for magnetic separation, but requires not only detailed test work, but also in-depth understanding of your ore body, an investment which can be absolutely invaluable. Thank you very much for your time in attending this presentation, where we've learned that grinding finer is not always the optimum solution, but with intrinsic knowledge of your ore can definitely add value to your process.